So we'd like an exploded view of that machine. So how many pieces do we got? We got 2, all right? So explode them, put them apart, and put them on the paper. And just, again, I'm not looking for a work of art here, just something, something functional that will work, okay? Find somebody you can work with, too. So separate the parts so they're not connected anymore. You have it like a stick. So the 2 pieces have to come apart. When they come apart, they're not quite in the proper orientation anymore. So 2 pieces, okay? Oh yeah, I'll staple those up. You can just lay it crosswise this one, because that's not stapled either. I've got a staple.
Okay.
Y'all done okay? So what I want are 2 pictures of that thing that are so I'm seeing that top jaw like that, and then it comes down, and then it flattens out. So there's a picture of the first one, the top one. That's what I'm looking for. Get the second one in there, okay? Let me see what you got. Alright, so get it drawn the way you see it. Just break it into 2 pieces. So 2 pieces, and just split them apart. So we don't want them connected, we want them separate. That's the whole thing with this framing machine stuff, is we want them as separate entities.
Like that?
Yeah. Yeah.
No, this should be an art competition.
You're just competing with yourself. That's all you gotta do. The best you can. Well, getting something there?
What are we doing now?
We are going to figure out what happens to this thing when we start pushing on it. Okay, so what we're going to do is we are going to create an exploded view. All right. Is that did I do okay? Now see how I kind of got the orientation of them too, right? See how that top one kind of has a right angle hook in it, then it drops down to the pin joint, then it angles out. We're good with that? And then the bottom one is kind of flatter. Even though it does have that horizontal platform, those are the things I'm paying attention to. So we got any questions on that? Because what we're doing here, we're going to analyze this framing machine, and step the first here is to break it up into pieces. That's how you do it, okay? And again, you don't have to exactly imitate the pieces, but you need the orientation of things, how they're oriented. Those jaws are horizontal, the arms are angled. That's kind of the important things on that. All right, so we got any questions on what I got there? Okay. All right. Now let's put the forces on there. We're assuming that the force on the grip is perpendicular to the grip. We're assuming the force on the flat surface is, we're kind of assuming it's smooth, which of course it's a ribbed jaw, it's not quite, but we're assuming that force on the jaw is perpendicular to the jaw. Okay, so get some forces on that. What do the forces look like? So with forces, we're just doing vectors. Just get them going the right direction. Think a little bit how they interact. How do the two pieces interact with each other? You know, we talked about that equal and opposite thing. All right, so I got a force probably doing that on the jaw. Would you all agree with that? So what's the force on the other jaw doing?
Opposite.
Yeah, and that's not a coincidence, is it? Because if the circular object here that I had, if it pushes up on the bottom, up top jaw, it's going to push down on the bottom jaw, right? Okay, so these things, you got to pick that up. That's, I'm saying that because it's an important part of analyzing these things, is getting that right, okay? Understanding that idea. Because they're equal and opposite. It's kind of like what you learn in physics, action and reaction. Okay, it's the same sort of idea. Okay, now we're going to assume that that's 20 pounds, which is something on the order of 89 newtons. So let's assume that. So, yes.
If the device was together, wouldn't the arrows be pointing the opposite direction when it was closed, like to clamp it?
It depends what you're drawing a free body diagram of. So that's a good question. I'm drawing a free body diagram of the pliers. So the round object pushes up on the top jaw and down on the bottom. They clamp in on the round object. The round object pushes back. Is that answering your question? Yeah. Okay. So I'm drawing what happens to the pliers. Okay. All right, now, we good with that? We doing all right? Okay. Now, how about at that pin? What's going on there? Let's say, I'm just going to assume that the pin forces are like that and like that on the top jaw. Why don't you put the pin forces on the bottom jaw? If I assume that, what will the bottom jaw look like? Now what I got there is that 20-pound push that I'm assuming, which is something on the order of 89 newtons. Might be a little less, I can't remember, but it's in the ballpark. Okay. So if I'm assuming that force on that top jaw from the pin is right and up, what would I assume on the bottom jaw? I think so, yeah. Opposite, right? So, and see, I'm doing this because it's important, because this is how we solve this stuff, by getting a decent free body diagram going. if you can do that much, you're more than halfway to solving it if you can draw a reasonable free body diagram of what you've got. Okay? So do we got any questions on what's going on here? Maybe I'll just call that point A, that thing in the middle. Call that B. Call that C. Well, I guess it would be C and D when they're different. You okay with that? Okay. All right. Questions? All right. So what I did, I measured everything out, and this is what I got. Okay. So there's the crucial dimensions, I think. So why don't we get those put those dimensions on your problem there, and let's get these forces going, like that, and like that, and then like that, and like that. Okay. And what do we got? These are 89 newtons, right? And did I give these a name? Was that A? So I'll call that FA, right? And then we got these forces at the pin, which I went up.
So David, I was curious.
Yeah.
On the photo?
Uh-huh. Oh, hang on just a second.
On the handle of the photo?
On the handle of the photo.
Like on so the handle on the photo, the forces are facing down on the bottom tooth handle, and then on your free body diagram, they're facing up on the bottom tooth handle.
Bottom tooth handle.
You see how the bottom side of the where it contacts, I don't know what to call it. That one, that arm, the bottom arm. So that arm, you have the arrow facing up on that arm, right?
Yeah.
Then in the next screen, you have the arrow facing down.
Did I
on that
switch
arm.
them? I switched them, didn't I? Thank you.
Because it's really easy because
Right.
they jump.
Yeah.
The top one is the top here.
Thank
and
you.
the bottom one is the
Yeah, I
top
screwed
arm.
up on my
The
exploded
bottom
view.
one is the top arm from the previous picture.
Yeah, right. Okay. Got it. So kind of like Ghostbusters, across the streams. You don't ever do that. Okay, there we go. Bring it back the other way. Okay, thank you. And this is correct now, right? Which that's kind of a problem with these exploded views.
It's like an optical illusion.
Yeah, kind of, yeah. Yeah, right. Because they actually cross, yeah. All right, thank you. So we good with that? Right, so why don't we figure out first what FA is? Okay. So what is FA? And just ask somebody, just work with somebody here. Let's find FA first. Looks like we're getting a good multiplication of force on this thing. And that's the whole point of these things, is to see your hands aren't strong enough to, turn bolts and do stuff like that, right? So we use these tools to amplify the force. So we do. Okay. So y'all get to that? Should be somewhere around 300 and some odd. How are you gonna find that force on the jaw, FA? What's the one-step program for doing that?
Take a moment about C.
Yeah, you see, and the deal is you've got a bunch of unknowns there at the pin, right? You got, well, not a bunch, you got 2 of them. But if you take moments about the pin, you don't got to worry about those. So that could be a very good strategy on machine problems, is take a moment about a pin. That way you eliminate the need to find those forces with your moment. Okay? So if you do that, you should be able to come up with that pretty quick because you have dimensions that are perpendicular to the forces. So that would probably go pretty quick to find those forces. Okay. Y'all all right with that? We got any questions? All right. So we called that point C. Is that what we called that? Oh, I called it B. I called it B. Okay, we'll call it B. So sum of moments about B. And of course, this is static, so that equals 0. And what we're going to have then is 89 newtons times the 16.65. Now, I could go into meters or stay in millimeters. It really doesn't matter. As long as you're consistent. Often I do like to get into meters, so maybe I'll just go into meters. But it's okay, especially on a shorter problem like this where all the dimensions are in millimeters. You could do that, but I'll just go into meters because I've done that a lot in this class. So that'd be 0.0601665 meters, and then I'm going to have my unknown FA. Okay. All right, so 0.004 FA then is equal to 89 times 0.01665.
Is that a minus?
Yeah, it's clockwise, thank you. So that'll be a minus, bring it to the side of the equation. Now it becomes positive, and then we multiply that by 89. We get 1.48 basically. And then we'll divide it. And that's FA, okay? So that comes out to be 370 newtons, near enough, okay? So we're pushing with 89 newtons. We get a clamping force more than 4 times that with this machine, 370 newtons, okay? So what's happening here is if that acts up at A, that'd be 370 newtons going up. It's acting down at B, or on the other side of A, I guess I should say. I'm calling that. All right. So we got any questions on that? All right, how about finding those pin joint forces then? What do we got? I think to accomplish that, we're going to go with X's and Y's. So I think we better know that angle right there. Is that right? I would think. Okay. And, I get intuitive about some of the things I do, but I don't get intuitive about geometry. That usually doesn't end well. So I'm going to make that a right angle in there. This is kind of like that roller on a ramp thing, where I'm going to have to figure out the angle that I can figure out pretty easily, which is the angle of that armature, because I've got the 2 dimensions there, okay? I can figure out that angle. And once I've got that, I'll basically take 90 minus that to get the angle of the force. That's going to be the deal with this one, all right? We doing right? You guys are kind of quiet. Got any questions, you know?
Oh, is it 36.9?
36 point, that sounds about right. I didn't work this one out, so I don't
It's
know.
like you use the rise at the 12.5 and the 11.
Yeah, it ought to be, yeah, okay, that sounds about right.
Okay.
Okay. So we'll just do an inverse tan. We get 48.65 here.
Oh, yeah, I got the wrong one.
Okay, subtract off 90. 41.35. Okay.
But and then you added 90 to it?
Subtracted it from 90. What I'm doing there, I mean, the long story on what I'm doing is this total flat line here is 180. I've already used up 48.65, and I've got a 90 in there. But see, the 180 and the 90 are always in there, so it's just 90 minus the angle gets you the other one, is the deal.
Okay.
And that comes out to be 41.35 degrees. All right, we good with that? We got any questions on that? Anybody got a question? You guys are paying me $400 for this. Come in here. You're not getting their money's worth. Well, this is supposed to be good value here. You should make use of that. You can ask me anything you want. That's fine. Yeah, question? You all right? Okay. All right, so, and I'm starting to, run out of room here to do this, but it would be a sum of fx and a sum of fy is how you would finish this off. So you go sum of fx equals 0. So what do we got? Real quick, we've got nothing at b. We've got negative, right? Cosine 41.35 times the 89. And then I'm over here, so I'm going to go plus fbx. Now, it is a good idea to name these because you want to keep track of which one you're working on, okay? So this would be, what I'm working on there is ABC. I'm sorry, I'm just running out of room here, so it's getting a little messy. And there's D down there. All right, so I could solve for fbx then, easy enough. And that comes out positive, and the positive answer I'm getting means my assumption was correct. It does act to the right. So I'm going to take cosine of that angle, and I'm going to multiply it by 89, and that's 66.8 newtons. Okay, and then real tight in here, sum of fy is 0. And what do I got? I got 370 up, and I've got minus sine of 41.35. I'm going to have to move that down a line because I don't got enough room to put it, but I guess I could put fby here. I got room for that. And then I'll put the minus sine 41.35 below, and that's times 89. And that should get me fby, although I think I guessed. Let's see what happens with this one. I'm not very confident that I guessed right on that one. So 41.35 times sine, and that's going to, let's see, times 89, and then I'll subtract off the 370 because that's going to the side of the equation. So I'm getting negative 311 for fby. So that negative sign, what that means is no, it's kind of a digital thing, positive is yes, negative is no. So the no means I didn't pick the right direction. That force at B actually goes the other direction. Okay. Yes, on the top, on the one I've drawn on the top, which is ABC. Okay? We good with that? Yeah, question there? My A is at the, it's the pipe, it's the thing I was grasping. So I'm using A to signify that where the contact with the flat jaw is. Okay. We good with that? All right. So that's 370, 89, and 66.8. So this is 66.8. This is 89. This is 370. That's 370. This one, what was that? The one that I guessed wrong on, 311. So 311 actually is going this way. It's going down, okay? It's 311. So what does that mean for this one? Oh, not that one. This one. What does that mean?
Stop.
Yeah, it's going up, okay? You got to remember to turn these things around as you go from one piece to the next. Okay, that's part of doing these frame of machine problems. All right? So this is 311 going up. This is 66.8. There we go. So that's what's happening with that thing. Now, once you got all that stuff, then you can design it. You can make it strong enough to do what it has to do. Now, you know, there might be a lot of things that go into the shape of it. You know, the part of it is the strength of it. The other part is I don't think you want these arms so narrow that they're hard to grip. You know, there's all these factors that go into this stuff, especially these days with ergonomics and ease of use and all that. But all the same, this gets you the first steps in designing this. And you notice the real weight of these things goes into the jaws, doesn't it? That's where they're putting a lot of the real metal on this.
Yeah, point B is movable.
Yeah, it is. And they got little ribs in there, see? So, you know, this is a good example of you know, the need to assume things when you start working. Is that a pin joint there?
Channel joint.
Yeah, it's, I don't know what it is. You know, it's got these ribs in here. So, you know, get over that when you start working. Just model it as something and go with it. Come up with some numbers. You know? These models we make when work, they're not perfect. That's not a true pin joint. It's really a slot, but also it's got those ribs in there that kind of hang it up and make it into a pin joint. So if I had to analyze that as something, I'd analyze it as a pin joint. And I'd use the safety factor of 2. I don't worry about it too much. And yeah, I'm kind of being facetious, but also I'm quite serious. You know, that's
You
how
could
life.
analyze each slot as its own pin,
Yeah.
and then you would know what its function was at each slot. I'm sure some engineer did that.
Well, yeah, maybe they did. You know, I don't know.
Yeah, they know what force it has in all the settings.
You know, I mean, you know, and again, one thing you do is you analyze everything. The other thing you do is you don't analyze everything, you double your answers. I mean, that's another approach. And, you know, I went out to my first job site with a set of blueprints. I'm a civil engineer, and they're nice, pretty blueprints. And I get out there, and it's a dang hole in the dirt, you know. So what it is a bunch of bulldozers driving around. It's not this pretty set of plans. It's a bunch of dirt with a hole in it, you know. You got to kind of understand that, you know. We analyze stuff, but the stuff we make and the things we do are just a little different, you know. So, for whatever that's worth. So are we good with that? Now, of course, when you're analyzing circuits, that's a different ballgame, right? That stuff's pretty much right on what you analyze. But when you're doing civil and moving dirt around, you can't model dirt. It's dirt, you know. You can come close, kind of in the ballpark, but it's a pile of dirt, you know. That's what it is. Mechanical's kind of somewhere in the middle, you know. Okay. So we good with that? That's a little bit on frames and machines there, okay? We'll look at a couple other variations of this. But that's the technique, okay? And you know, that's often what I try and focus on here, right? How do you do it? That's how you do it. You take it, you break it up into an exploded view. You break the pieces out. Then you assume forces on the pieces and you work between the pieces to solve out all the forces. This one is rather simple because each piece can be solved independently. But also we had that little thing here where once I found out that was down, that meant the other one was up. The pieces interact, okay, and you have to consider that, right? Okay. All right, so we did one of these on Friday. Let's see what else we can do. We ran through this one. Or did we? No, I think we did. Let's back up here a little ways. So let's look at the next one here. Let's look at pulleys and how we handle those. We did a frame. That's what we did on Friday. We went through this thing, and we did a process similar to what we just engaged in here. We broke it up into pieces and kind of worked our way through. Let's kind of go to the next step with pulleys. Now remember, the deal with pulleys is that the dimensioning on pulleys can get kind of tricky, because if you've got cables coming off at angles, that makes finding that exact coordinate on the pulley kind of hard, where that point of tangency is where you want to apply that force. So the trick is to take the forces from the cables on the pulley and put them both at the pin. It makes the dimensioning much easier. Okay, so that's the deal. That's how you approach that. So let's look at something like this. So I'm on page 580. So what you want to do on this, again, you want to break it up into pieces and make a free body diagram. Now on this problem here, another part of breaking these up is to look for two force members, because you can simplify their analysis, okay, on your exploded free body diagram. So that was a two force member, okay, BD. However, not all frames and machines have them, so don't invent them. If you don't see one, there may not well be one. If you see a two force member, you want to identify it and just treat it as a force, kind of like a truss member. But here, I'm looking at this and I'm seeing 1, 2, 3 points of contact on ABC, and then on DCE, I'm seeing 1, 2, 3 points of contact. So I don't think I got any two force members, because two force members obviously have two forces. This has the opportunity for 3 on each one. So I'm not going to pull a two force member out of that. Okay, I've got the angle of the cable there. It's 26 degrees. So I drew those two exploded views for you. The horizontal, ECD, and the angled one, ABC. Okay. So let's find the forces acting on ABC. And let's just do it. I often don't bother with reactions on frames and machines. They often don't get you very far, and on some of them you can't really do much for reactions. So let's do this without reactions. All right. So let's get some forces on here. So what do we got? Pin joint at A, so AX and AY. Got the cable force at B, and then I've got a pin joint at C. Okay. So I got CY and I got CX. Okay, at D, what I've got is DX and DY. And that's a pin at C also, so I got CY and CX. Okay, something like that. And then I have that cable force running through there as well. So on the last one, it was pretty straightforward in that we had each unknown with, well, one of the unknowns had, or one of the members, one of our pieces on our exploded view had 3 unknowns. So you can solve that with statics. But on this one, I don't know if I can, because I know what T is. T's right there, 6,000 newtons, okay? So T is a known, 6,000 newtons going either way. But still, that leaves me with 4 unknowns on either piece. On the horizontal one, DCE, I got DX, DY, CX, and CY. And on the angled one, I got AX, AY, CX, and CY. Okay? So that means I got to do a little bit more thinking here. Do you see any opportunities where I could solve for one of those? If I can just get one, I can start to work through this, I think, but I'm going to have to get one. I got 4 unknowns on both, which is statically indeterminate by definition, because these are 2D problems. But can I kind of cherry pick one of those? Is there one of those I can get?
CX and CY on both of them, so you can solve.
Okay, that's a good point. If I get one, I can flip it and put it on the other. Then I got the other down to 3 unknowns. But I still got to start somewhere.
CX and CY first.
Okay, how could I get CY? What would be the magic equation to do that?
In a moment.
About
A
about A.
or B.
Okay, now which one's the simpler of the 2 pieces?
Oh, a moment about D would be really easy.
Yeah, there you go. And see, that's simple because it's horizontal, right? It's laid out nice and square with vertical and horizontal forces.
So you only care about the sign.
Yeah, now if I did moment about, and I can do moments about D, and that'll be enough to get CY, won't it? Now notice this one is not the same because it's angled. I couldn't do a moment about A. I'd still have 2 unknowns, CX and CY. So notice that the place to start is on the horizontal one because all those 3 of those forces go right through D. So I can eliminate them if I take a moment about D. So look for things that are horizontal and vertical if you're in a spot like this. You can often kind of cherry pick one unknown from them, okay? So you can find a way to get one of the unknowns. So this one is a little bit more kind of strategic than the one we did on Friday. Oh, here we go. I was wondering where that was. Okay. So there's my free body diagram. You know, I needed to include this downward 6,000 here also, so I've got that on this sketch. Okay, because what's happening here, I got this 6,000 Newton force, so that's doing that, it's also doing that, and then it's doing this, okay? That's how I'm analyzing that, okay? So I have to include both of those on there. And then I've got those forces at D and C now. So what I'm going to do is take a moment about D, and that will get me what I want, which is CY, I think. So sum of moments about D, and I'll set that equal to 0. And what do I got? I've got CY times 1.1. And then I've got minus 6,000 newtons times 1.1 and 0.7, that's 1.8 meters. And then plus sine 26 times 6,000 newtons. Same moment arm, 1.8 meters, I think. Okay, does that look about right? All right, we can go ahead and work through that and get CY. That would be the first thing to do. So I'm going to have that 1.1 CY all by itself on one side of the equation. I'll take the other things to the other side of the equation. So 1.1 FCY, and that will be 6,000 times 1.8, and that's 10,800. And then I'll subtract off 6,000 times 1.8 times sine 26. And that's 4734. And based on that, I ought to be able to come up with FCY. I think it's 5514. And I think it's in the direction assumed. Okay. We all right with that? And the idea, we found the horizontal one. That allowed us to go about D and solve for one of them, CY. Now I can't solve that whole thing out because there's 4 unknowns, but I can get one thing. Now I'll take that to the other side. See, I'll take that up to that other bracket, start to use that, and kind of work them against each other sort of thing. That's another strategy on these more complicated ones. You okay with that? That's the deal, all right? So I just found that CY is 5514. So what's it going to be over here? It's going to be up or down?
No, down.
Yeah, it's up on this one, so down on the other, okay? That's how it goes. Okay. So you want to keep track of which way they're going and which part you're talking about. So now I've got that. Now I'm down to 3 unknowns on that top one, ABC, so I can start to work through that. Now I'm going to have a little bit of a complex moment problem, but you know, it's fine now. But I'm down to enough unknowns where I can figure out ABC as I need to, okay? So this is another little trick on these frames and machines. The idea here is we're kind of bouncing back and forth between the two. We found the 5514, which somehow I turned into 5515 over here. Not that it makes much difference, but we'll leave it at 5515. I'm not quite sure why I did that, but I did. Okay, so now I can take a moment about A and find CX. It's 13616. All right, so we're doing okay with that. Then I do a moment about A. I got sine of 26 times that 6,000. Now I'm on ABC now. Notice I'm marking where I'm at because I want to be sure that I'm clear on that. Okay, ABC. So I got sine of 26 times 6,000. That's negative because it's times 0.8 meters. That's a clockwise moment right there. That's why that's a negative. And then I've got the 5515, which used to be 5514, and it's not a significant change, but I even overwrote it, so I'm not sure why I did that, but it doesn't really matter. It's just 1 Newton out of 5,000, so it's not a big deal. 5515 times 1.1, that's negative also, so that's this one that's coming around that way. And then you'll notice I got CX over there. That's an X force, multiply it by a Y moment arm, right there, the 0.6. And the CX, and that's getting me another clockwise one, so that's minus. So I'm noticing I got an awful lot of negative stuff in that equation, so sure enough, I got a negative answer. I didn't assume CX in the proper direction. It doesn't act to the left on ABC, it acts to the right to hold equilibrium. And it comes out to be 13616. Now notice that I assumed it's left. I got a negative answer, and the negative answer means it actually acts to the right, okay? So that illustrates that difference in signs and how you use them, okay? They go into the equations to indicate the direction you assume things act, but the positive or negative answers means you're right or not. In this case, I was not. It does not act to the left, it acts to the right. Okay, that's what's going on there. All right, so that's the forces on ABC. You got any questions on that? I'm doing all right? Okay. So what we're doing here, with the trusses and now with this, is we're just using the skills we kind of developed when we did equilibrium, and now we're applying it to a little bit more complicated things that are kind of tied together, okay? So that's all we're doing there. We got these steps that precede using the equilibrium. That's what's going on now. So the important stuff on these frames and machines is pull them into parts, identify the two forces if there are any, and then remember to switch the direction of the forces as you work your way from one connected piece to another, okay? You'll want to take a break here for 5 minutes.